So today we'll be going through the monotonic sequence theorem. We will not be doing the proof for this, so you don't need to worry about that. However, the applications of using it, that will be very important for the quiz next week, for the test coming up, and the exam. Okay, so you will see this in all three. Now, before we get to the theorem, there's a few definitions we need to go through. Okay, very simple definitions, but you do need to know what these mean before we get to the main theorem. Okay, so the first thing is increasing. So a sequence AN is called increasing if AN plus 1 is greater than or equal to AN for all n. So very simple definition, but we say that a sequence AN is increasing if the next term is greater than or equal to the previous term. That makes sense, right? Increasing, so the next term must be larger than the previous one. Number two, strictly increasing. A sequence A sub n is called strictly increasing if AN plus 1 is greater than AN for all n. So you see here for strictly increasing, we don't allow the next term to be equal to. Okay. So for increasing, it can be equal. For strictly increasing, it must be strictly greater than, cannot be equal to the previous term. Number three, decreasing. A sequence AN is called decreasing if AN plus 1 is less than or equal to AN. So the next term is smaller than or equal to the previous term. Then number four, strictly decreasing. You can guess what that means. Okay, so a sequence AN is called strictly decreasing if, very similar to the other case, AN plus 1 is smaller than AN, and it can't be equal. Okay, it must be smaller. Again, for all n. Yeah, very simple definitions, but please note the difference between increasing and strictly increasing, and then decreasing and strictly decreasing. Okay, very small difference, but we'll see later that is important. Yeah, a few more definitions. So number five, bounded above. Okay, a sequence AN is called bounded above if there exists a capital M such that AN is less than or equal to capital M for all n. Okay, so it's bounded above if the sequence doesn't go above that maximum value, capital M. And then just note, this capital M is not unique. So you can pick anything larger than capital M, and it will still be an upper bound, right? So any capital M will do. Okay, there's not a unique one. I'll just make a note here. This capital M here is not unique. Okay, so anything larger than that is also a bound. Okay, and this capital M is called an upper bound. Okay. Number 6, bounded below. Okay, what is that talking about? Okay, there shouldn't be any talking. A sequence AN is called bounded below if there exists, now we call it a little m. So capital M, that's for the upper bound, it's large. And then for the lower bound, for bounded below, we call it little m, right? There exists a little m such that little m is less than or equal to an for all n. Right, we see it's bounded below because any element or term in our sequence is not smaller than this. Okay. So we say that is a lower bound. It doesn't go below that little m value. So little m is called a lower bound. And again, it's not unique. Right? If you have a little m that satisfies this, anything smaller than little m also satisfies this. So again, it's not unique. Right? Anything smaller also counts as a lower bound. Yeah. And finally, number 7, bounded. Okay, so please don't mix up this terminology. So we have bounded above, that's one thing. Bounded below, that's another thing. And bounded, that's a third thing. Okay, so that you can't use them interchangeably. It's three things. A sequence AN is called bounded if it is bounded above and it is bounded below. Okay, must be both. So if I say a sequence is bounded above, then it is only this first. It is only this first one that we know. Okay. So specifically bounded above is only this. Bounded below is only this. Okay. And then if I say it is bounded, that means it's both. So you need to be careful about if it's bounded above or bounded. It's two different things. Okay. So that's it for the terminology we need. Any questions about this? You're all good. Okay. So the theorem. Again, we won't be going through the proof, but you will need to know the applications of it. So this is the monotonic sequence theorem. Every bounded plus monotonic sequence is convergent. Okay. So we know what bounded means, bounded above and bounded below. Okay. Monotonic, that means the sequence is either always increasing or always decreasing. It can't be a combination. So mono, meaning one, so it's one of the two. It's either increasing or it's decreasing. It can't be a mix. So here, mono, meaning one, either always increasing or always decreasing. Not a combination. And we'll see some examples and non-examples of this. Okay, examples and non-examples. Okay, so number one, let's say we have the following sequence like this. Okay. So we see that the sequence here with the dots is decreasing. Okay, so that's first thing. And second, it's bounded below by that little m. So it's decreasing and it's bounded below. Therefore, we know from the theorem that it is convergent. So decreasing plus bounded below means it's convergent. And we didn't have to check for any limits. Okay. Okay, so all we need to check is that it's decreasing and bounded below, and we automatically know it's convergent. No need for any limits to be done. Number two. Here we see that this sequence is increasing and it's bounded above, so it's convergent. So if you can show that it's increasing and it has some upper bound, then we already know it's convergent. Again, you don't need to do any limits. We know it's convergent. We don't know the limit value, okay? But we do know it's convergent. And number three. Here we've got this sequence. We see that it's bounded above. It doesn't go above that capital M, but it's not increasing and it's not decreasing. We see sometimes it's increasing, sometimes it's decreasing, but that doesn't mean anything. It has to be either increasing all the time or decreasing all the time. If you have something like this, you can't say. So here it's bounded above. But it is not monotonic. So we can't say anything. Right? Might be convergent, might not be convergent. We don't know. Okay, so again, only if it is bounded above and increasing, it's convergent. Bounded below and decreasing, convergent. If either of those conditions are not met, can't say anything. Okay. Now, very important note, when I say can't say anything, it means we can't decide between the two. It does not mean it's divergent. Okay, so bounded plus monotonic means convergent. If one of those two are false, it does not mean it's divergent. Okay, so please just keep that in mind. All it means is we don't know. Any questions for these three examples? Okay. Please make sure you pay careful attention to when you can use it, when you can't use it. Right. Any questions before we move on? Yeah. Oh, you can't say. Remember here, you can only have a conclusion for these first two. So if it is increasing and bounded below, it doesn't mean it reaches anything at the top. For example, let's have that over here. So number 4. So here it's bounded below and it's increasing. Right? This is divergent. We can see that, right? But you could also have something like this. Something like that. This is convergent, but we haven't stated any upper bound, so we can't say anything. So again, it's either this first one, decreasing plus bounded below, or the second one, increasing, bounded above. Any other case, we cannot say which one it is. Okay. Yeah, so 1 and 2, we can get a conclusion. 3 and 4, there's no conclusion. We cannot decide between the two. All right. Any other questions before we get to the examples? Okay. Yeah. So let's have a look at the actual calculations. Okay, so the question will always be phrased in this kind of way. So use the monotonic sequence theorem to prove that the sequence A sub n is convergent. Yeah, so it will have this kind of phrasing. Of course, if you use another method, you're going to get 0 because the question says use the monotonic sequence theorem. Right? So please follow what the question says. Yeah, but it'll be very clear in the quizzes, tests, and exams on what you should use. If I do not include that, then you can use any method or sequence proof that we've done before. Right? Your limit laws, squeeze theorem, L'Hopital's rule, all of that other stuff you can use. But if I specifically say use the monotonic sequence theorem, then you have to use that. Okay, so number 1. We have A sub n is equal to 1 minus 1 over n. So very simple, just to get us started. So what we need to do is figure out which case is this, right? It's either case 1, where it's decreasing and bounded below, then we know it's convergent, or it's increasing bounded above, we know it's convergent. Anything else, we can't say. Okay, so it must be one of the two. So if I just give you this, we need to check, is it increasing or is it decreasing? So let's check. Okay. So A1, what will that be? Okay. More than just one person, please. A1? 0, thank you. A2? Half. A3? 2/3. And so on. You can add a few more, but we see the pattern here. 0 to a half to 2/3. What's happening? It's increasing. Okay. So we need to show that it's increasing and bounded above. That means it's convergent. So 2 things we need to show. Number 1, we need to show that it is increasing. And number 2, since it's increasing, we need to show it's bounded above. It's no use showing it's bounded below because we know it's increasing. Okay, so let's write down what these 2 mean so we know what we're aiming for. So increasing, we need to show that the next term is larger than the previous term. And for bounded above, we need to find, right? We need to calculate some capital M that's larger than anything in that sequence. Okay, so there are 2 steps that we need to follow. In the quiz, I will break it down into the individual steps. So step 1, is it increasing or decreasing? Showing it's increasing, showing it's bounded above, and then the conclusion will be broken down into those steps. For the test and the exam, I will not give you the steps. I will just say, show it's convergent. You then need to provide the steps. So number 1, showing it is increasing. So I will show you 2 methods of showing that this is increasing. Depending on the problem, one of the methods would be better than the other. Okay, that will be up to you to decide. So for this one, I'll show you both. And then again, depending on what you get, you can pick between the 2. So method number 1. So method number 1 is building up an inequality. So we're going to start with some starting points, and we're going to build up towards this inequality over here. Okay. So what can we do? What we want to show is that this an given over here is smaller than an plus 1. That's what we want to show. Okay, so again, we want an plus 1 to be larger than an. That means it's increasing. So if we actually substitute that, what we want is that 1 minus 1 over n plus 1 is greater than or equal to 1 minus 1 over n. That's the goal. That's what we're trying to do. So we need to find some starting point such that we get to that. So again, this is just thinking. Now time for you to get some points. That's what we're thinking about. We need to get to that step over there. So we need some starting points, and then we build up, and we end up with that thing in pink. So 2 points. Where should we start? Okay, that's the goal. We need to start somewhere. There's lots of starting points. Yeah. Sorry? No, that's not a starting point. Anyone else? Where can we start? Well, yeah, that's what the bonus points are for. Yeah. Yeah. So, have you missed a lot of lectures? Okay. Yeah, no, I mean, just shout out. That's fine. Yeah. Well, no, don't look at that. That's what we're aiming towards. We need a starting point. So we're not changing that. We're trying to get to that. Yeah, don't look at that yet. Yeah. Yeah, we're not changing anything there. Yeah, in the back. Might. Okay, not quite. Yep. Okay, quiet, please. N plus 1 is greater than or equal to n. That's a good starting point. Remember, it's not just one starting point. You can have different ideas, but let's see where that goes. Okay. We don't know if this is right yet. We'll see. Okay. So this is more thinking, I guess. Okay, but we'll see where it goes. So you don't get your points yet because it might be wrong, but we'll see. What do we do next? So that's a good starting point because we have that in the denominator, but that's not in the denominator yet. We need to get there. Okay. Does everyone see that? Okay, so those are the two denominators, but it's not yet in that form we want, in the pink cloud. So what do we do? Not greater than or equal to, less than or equal to. But yeah, that's fine. Okay, let's see how that goes. So she wants to take the reciprocal. That's good. Looks good. Okay. Remember, the inequality swaps. 3 is bigger than 2, but if you swap them around, a third is less than a half, right? It swaps. Good. So that's getting close to what we want in the pink there. There's some stuff we still need to do, but that's fine. Introduce the negative sign. Okay. Now this will also flip the inequality, right? 2 less than 3, minus 3 less than minus 2, right? That looks good. Almost. And we can put a 1 on both sides, yeah. That doesn't change the inequality. If you add 1 on both sides, it stays the same. Looks good. What do we have on the left? This is an plus 1. Right? We put n plus 1 in the bottom. And now we're saying this is greater than or equal to, what do we have on the right? An. And we're done. Because we showed that the next term is larger than the previous term. Very good. Okay, well, you gave the whole step, so you get a few more points. Yeah. Okay, good. So that's method 1, building the inequality. We can do something like that. Now, she started with this. Okay. but maybe you have another idea for a starting point. Okay, that could also work. Yeah, so it's not a unique starting point. Maybe you want to start with n is greater than or equal to 0. Right, that's somewhere to start. Yeah, you can do that as well, because we know n is a natural number. So you could say n is greater than or equal to 0. Maybe you can build up from there. Again, it's not unique. You can think about that there. Okay, so maybe you think of something else. Try to do that as well. Okay. Good. So that's method 1, building the inequality. You can do it that way. Let's have a look at method 2. Method number 2. Now, please don't go and do it both ways in the tests. Okay? Just pick one and go with that. Method 2. Using derivatives. Now, this one comes with a very big warning sign. Okay, so I'll get to the warning sign in a bit. But the idea of using derivatives is replacing the sequence with a continuous differentiable function. Okay, maybe I should put 2 warning signs. There's 2 things that you need to worry about. Replacing the sequence a sub n with a differentiable function. So we write it as f of n, where f is a differentiable function. Very similar to what we did last time, where we replaced the limit with n with the limit with x. Differentiable. If it's not differentiable, you can't do the derivative, and this doesn't work. Okay, if f of x has f prime of x greater than or equal to 0 for all x greater than or equal to 1, okay, we start at 1, then if it has a positive gradient, it's increasing. And if f is increasing on the right, then an is also increasing on the left. And this works for decreasing as well. We just swap the inequality there. If f of x has f prime of x less than or equal to 0 for all x greater than or equal to 1, then an is decreasing. So that's decreasing. So let's have a look at this for our problem of 1 minus 1 over n. And then I'll show you another example where this won't work. So we have an is 1 minus 1 over n. So all we do is we write this not as a sequence with n, but as a function with x. Okay. We replace n with x. So let's check, is this differentiable? Yeah, it's differentiable. That's fine. So we can do the derivative. So f prime is going to be 1 over x squared, which we know is always positive. So f is increasing, so the sequence is also increasing. So we replace our sequence with the function, And if the function is increasing, then the sequence is also increasing. But now for the other warning sign. So the first one we know. Okay. Let's say we have an is minus 1 to the n over n. Okay. Now, if we try to do the same trick, replacing n with x, we're going to run into a problem. Is that differentiable? No. No, you can't do anything with that. So this doesn't work. Okay. So you need to check, can you actually work with this function f? The same thing applies to that limit thing we did last time. If you replace your sequence with the function, but you can't do any calculus with the function, that's not going to work. Right? Like L'Hopital's rule. So please check before you start changing things to functions. So you can pick between method 1 and 2. Maybe you've got another method, that's fine as well. But these two work most of the time. Okay, so that was number 1 done. We showed that it was increasing. Number 2, we need to show that it's bounded above. If it's bounded above, we're done. So let's go back here. So we've got this over here. Now we can add more and more terms, and that will give us an idea of what the upper bound should be. Any guesses? Who said that? Good. Yeah, 1. We see that it's increasing, but if you just put in your calculator, you can add a few more. It will get closer and closer to 1. But it never goes past 1. So that means 1 is an upper bound. You could have also said 2, or 3, or 4, or 5. Any of those are upper bounds. Okay, so number 2, finding an upper bound. So we have an is 1 minus 1 over n. And we know that just adding more terms to the working we had earlier, it gets closer to 1, but never goes past 1. It must be an upper bound. So an gets closer to 1, but never past 1. Which makes 1 an upper bound. It never goes past 1. You could have done the same thing with anything larger than 1. 2 works, 3 works, 4 works. Anything larger than 1 is also an upper bound. So let's show this. Yeah. So we want to show that 1 is an upper bound, which means we need to show this inequality over there, with capital M being 1. Yeah. So same sort of game as before. We need some starting points, and we're going to build up to that inequality there. So again, let's think about where to start. Okay. Again, that's the goal, same as last time. So we need some starting point, we do some work, and we should end up with that inequality, right, for it to be bounded above. Okay, more points. Where do we start? Same as before, we need some starting points. Again, it's not unique. You can think of anything to start with, but some starting points are more helpful than others. The same? Means something.
Yeah.
N is less than or equal to 0. No, n is positive. N is always positive. So remember, n goes 1, 2, 3, 4. It's always bigger than or equal to 1. Yeah. Yeah. Raise your hand up.
How much for in
No, n greater than 1.
one?
Okay, let's try that. Now you don't get the points yet. It must still work. So again, we're thinking. So n greater than or equal to 1. Okay, good enough starting point. Let's see if it works. So that's our starting point. We want to get to the thing in pink. So let's see if you get the rest of your points. What do we do next? Take the reciprocal. That's good. So greater than or equal to becomes less than or equal to. Sorry? The minus, okay. Plus 1. Okay. Right. Let's see. Okay. We accidentally showed it was bounded below. Okay. So that doesn't work. I'll show you the fix for it, but just keep this in mind for. Okay, so we thought of something like that. Now the problem with this, I'll show you what it is. We assumed n was greater than or equal to 1, which is correct. That's fine. But the problem is that when we take the reciprocal, the inequality changes once. Then when we put the minus sign, it changes a second time. So if you put n is greater than or equal to 1, you do the reciprocal and the minus sign, you end up back with greater than or equal to. What we want to show is that it's less than or equal to. Right? That's the problem with this. So problem. Okay, now please make sure you include this. It's a very, very common mistake for the tests. So problem, the inequality changes twice. Therefore, you accidentally show a lower bound. Okay. Very, very common mistake. So let's fix this a little bit. Instead of having n is greater than or equal to 1, what is something better to do? Who said that?
Yeah.
Wait? Yeah, 1 over n. Good. So if you don't put your hand up, I don't know where the sounds funny got. Good. 1 over n. Yeah. Now you don't get all your points just yet. We need to see if it works. Put your student number, and then we'll see how many points you get. So this is attempt 2. Of 1 over n greater than or equal to 0. Sounds good. Okay, what do we do next? Yep. That doesn't do anything to the 0, so that's fine. And then we add the 1. Very good. now we showed it's an upper bound. Okay, does everyone see that? Okay, so please okay, be very careful with what you're actually trying to show. Don't accidentally show it's a lower bound when you need it to be an upper bound. Yeah, so you need to be careful. Yeah, that works. You get all your points for that. Good. So we've showed that it's increasing, number one. We've shown that it's bounded above, number two. Therefore, it's convergent. So increasing plus bounded above, it's convergent. Done. Okay. Now, obviously, this took a long time, right? Writing it out here. In the test, it will be a bit quicker than that. Please do the tutorials. It will help a lot. But this will be between 6 to 10 marks, depending on the difficulty. Okay. The reason is it's the different steps you have to do. So increasing is like one step, maybe 3 marks. Showing it's bounded above another step, maybe 3 marks. So it'll be like 6 to 10 marks. Okay. Let's put down the homework and then we can go. Oh, good. Please do the homework problems. The quiz questions, the test questions, and the exam questions tend to be homework problems. And of course, the more homework you do, if I give you something unseen, you already know a good idea of where to start. Okay, number 1, an equals n2 to the minus n. Number 2, an equals n over n squared plus 1. Number 3, an equals 1 over n plus 2. I think, yeah, just these 3. Actually, wait, number 4, but I'll put a star here. It is more difficult, but you can try it out. For number 4, we have a recursive sequence, like you did in the TUT. So this one is a1 equals 2. An plus 1 is 1/2 an plus 6. Okay, it's a little bit more difficult, but you can try that out. Okay, so the question is, use the monotonic sequence theorem to show that these 4 converge. Okay, so some of them will be increasing and bounded above, others will be decreasing and bounded below. You need to figure that out and then fill in the details for the proof. Right, any questions? All good.